So the inverse form of the translation theorem. So now we're going to transform of a function translated or shifted at s minus a. All right. Okay. If you want to reverse the notation to say s going to s minus a, you can just do that. That's fine. And then simply find the inverse transform of the function you have over there. And in the end, just multiply by e to the at, which is the opposite in sign of the translation. All right, that's all we're going to do. Okay, so, well, all we're going to do. So here's the thing. Okay, let's find the inverse transform of 2s plus 5 divided by s minus 3 quantity squared. Okay, at first glance, you can see some translation here in the form of s minus 3. So somehow, this translation theorem, we have a case for this translation theorem. However, the translation has to be present in every instance of x in your function to find the inverse of. That is, for instance, if you see this s right here, that's just 2s. So there's no s minus 3 translation. So what about it then? We wish it were s minus 3. We can make our wish come true, of course, right? This is the inverse transform of 2 times, okay? This is s minus 3, why not? But if we're subtracting a 3, add a 3, all right? Add a 3 and then plus 5, all right? And then that gets divided by, what is that? S minus 3 quantity squared, okay? So that's, we're presetting this to make it work like this. Okay, now here let me do some highlighting here, very important, very key here. Okay, so I'm going to highlight the translation we desire like this: s minus 3 with the s minus 3, and I'm going to use a different color to just highlight the other constant term. Why am I doing this? Because I'm going to distribute these two over here over, yes, technically there are three terms, I agree, but by highlighting this, that makes it two terms essentially. So 2 times is minus 3 and 2 times 3. All right, what is that going to be? Okay, so this will be the inverse transform of 2 times s minus 3, 2 times 3 plus 6 plus 5, everything divided by s minus 3 quantity squared, okay? And then what's next? Well, let's combine 6 plus 5, that equals 11. And this would be the inverse transform of 2 times s minus 3 plus 11 over s minus 3 quantity squared, okay? So in this case, I'm going to use the split up trick here. I'm going to I'm going to split the fraction. Well, it's really not a trick; it's algebra. So I'm going to take these two and multiply with the inverse transform of s minus 3 over s minus 3 squared, okay, plus 11 times the inverse transform of 1 over s minus 3 quantity squared, okay. Now, here's the thing. For the first term, we have a power of s minus 3 in the numerator that could be canceled with one of the powers in the denominator. Okay, so that's 1. And that is 2 times the inverse transform of 1 over s minus 3. And actually, this is going to be a very straightforward one. No, there's no need for a translation theorem, you know? Now, for this guy right here, I'm going to need to use a translation, you know? So, in this case, that's plus 11 times the inverse transform of, what is that? 1 over s squared. And then once we evaluate this, once we find the inverse transform, that's going to give us the desired result. Okay, so So the inverse transform of 1 over s minus 3, so that equals 2 times, this is an exponential one, 2 times e to the 3t plus 11 times the inverse transform of 1 over s squared. Well, 1 over s squared, it's the transform of just t, right? But well, because of the s minus 3 multiplied by e to the positive 3t. All right? Well, actually, there's not much to do right here other than, 11t e to the 3t. And that is the inverse transform. All right? All right. What about letter B? Okay, letter B will be a little bit more involved, because look at all the s's we have right here. So we have s over 2, we have an s squared plus 4s. Well, actually, at first glance, there's no translation at all, right? There's no translation to compare like we did with the previous example here, right? So, okay, but we're going to create such a translation. So we have this quadratic polynomial in the denominator. I'm going to complete the square, actually. So let me do some side strip below. S squared plus 4s plus some number that completes the square plus 6 minus another number that completes the square, because if we add, then subtract. All right? So to complete the square, we divide the middle coefficient by 2 and then square. In this case, that number is going to be 4. Add 4, subtract 4, so you can have the same expression. All right, so these first three terms will be the expanded form of a perfect square trinomial. That is s plus 2, quantity squared. 6 minus 4 is that plus 2. So what do we have right here? We have the inverse transform of uh, s over 2 plus 5 over 3 divided by s plus 2, quantity squared, plus 2. All right. So now it seems like we're going to have a translation of s plus 2. Okay, yes, we have it here. However, what about the one over here, the s? Again, we wish this were s minus s plus 2. All right, of course, again, we can make our wish come true, add and subtract the same quantity. All right, so this will be equal to, find the inverse of the quantity. Okay, let me put the 1/2 in the front this time. S plus 2 minus 2 plus 5 thirds. All right, s plus 2, quantity squared, plus 2. All right. Okay, again, let me take the same highlighting approach here. So let me highlight the s plus 2, our shifting with the same color as before, and the 2 here. All right. So let me distribute. Okay, do the algebra and keep whatever works. Okay, so number one, this would be the inverse transform of, inverse transform of 1/2 s plus 2, and then 1 times negative 2 is that minus 1 plus 5 thirds, everything divided by s plus 2 squared plus 2. All right. Okay, so finally we have the translations the way we want it here. All right, so let's see about it. So number one, let's combine like terms. So what about 5 thirds minus 1? That's the same as saying 5 thirds minus 3 thirds, which is positive 2 thirds. All right, so this will be the inverse transform of 1/2 s plus 2 plus 3/2, 2 thirds rather, not 3/2, 2 thirds over the same s plus 2 square plus 2 plus 2. All right. Here is where we will split up. Okay. I'm going to use the linear property, if you will. So a coefficient times the inverse operator times a term, or well, times a factor to make a couple terms later. So that'll be 1/2 inverse transform of, what is that? S plus 2 over S plus 2 squared plus 2, okay, plus 2/3 times the inverse transform of 2/3. Oh, wait, no more. Yeah, that's simply 1 over S plus 2 squared plus 2. All right. Okay, so at this point, guys, this looks crazy. I agree. Let me do the shorthand notation so we can easily find the inverse transform. I mean, actually, we have this ready to do it in one shot. Okay, so what is this about? So this means we will translate S at S plus 2, which means we will have a we will have a factor of e to the negative 2t at the very end. Well, actually, this takes into account for both. Well, let me put it like in the middle. So, okay, this takes into account for both. Okay, now, I'm going to denote 1/2 inverse transform of s over s squared plus 2. And then I'm going to say s going to s plus 2, right? But I'm running out of space here. Let me make this a bit smaller, make some room. Okay, so, okay, that is 2/3 the inverse transform of, what is that? 1 over s squared plus 2, also where s goes to s plus 2 as well. All right. And I mean, look at those expressions. Those are easier to find their inverses, right? So, but not yet, not quite yet. This one, yes, that's going to go to cosine. This one is going to go to sine. However, when we have the k squared here, for the numerator, we have to have its square root. So that means we wish we had the square root of this term right here in the numerator. It's not there. Well, of course, we can make our wish come true. Yes, multiply by root of 2, provided you divide 1 outside. All right. Okay, so the inverse transform of s over s plus 2, that'll be number 1/2 times the inverse transform of this, which is, what is that? Cosine of the square root of 2t, okay? And the space I left here is for this exponential e to the negative 2t plus 2 over 3 root of 2, okay, the same, e to the negative 2t, and that'll be the inverse transform, which is of sine root of 2 times t. All right, and that's about it. That's the inverse transform. All right. So yes, guys. So when we have an expression such like this, first we need to figure out what the translation is by completing the square on the quadratic polynomial in the denominator. Once we get that translation s plus 2, that means with every other instance of s, make sure to shift it by the same s plus whatever number, in this case s plus 2 here. All right. Okay, so how about we apply this to find, or rather to solve a differential equation, um, but I mean in where the first translation theorem would be involved. So they're asking us to solve the differential equation, y double prime minus 6y prime plus, what is that? 9y equals to t squared e to the 3t. All right. Okay, guys, if we were to solve this problem using undetermined coefficients, actually, this is a good case for undetermined coefficients. Well, you can see by the coefficients, the characteristic polynomial will have repeated solutions, right? So And then this may be a little problem. Well, actually, no, that'll be fine. We wouldn't need to multiply by t, but we would have to find how many derivatives, two derivatives of two product rules there, right? So, and then on top of that, solve the initial value problem. Well, with the Laplace transform, we can avoid all that. So let's find the transform of the second derivative, or rather minus 6 times the Laplace transform of the first derivative plus 9 times the Laplace transform of y, which is, what is that? Equal to the Laplace transform of t squared e to the 3t. Okay, so if you look at the right-hand side of the differential equation, that is the non-homogeneous part of the problem, that's its transform will require the first translation theorem. So we will take the Laplace transform of t squared, but because of the e to the 3t, we're going to shift it to as s minus 3, all right? So actually, let me preset that up, like in this case, a equals to 3. This means s goes to s minus 3. All right. And well, yeah, that's going to be our translation. Okay. So the transform of the second derivative, what was that? S squared y of s. Okay. So these y's are functions of t or functions of x, if you will. And then whatever we get are functions of s. All right. Minus s y of 0 minus y prime of 0. So that's the transform of the second derivative minus 6 times the transform of the first derivative. Let me use brackets for this. S y of s minus y of 0 plus 9 times y of s. Okay? And in this case, for the right-hand side, we're just going to take the transform of t squared, and whatever we get, s goes to s plus 2. Oh, no, s minus 3, right? All right. So, oh yes, let's substitute what we have. So let me highlight the initial conditions. Number one, y of 0 equals to 2, and y prime of 0 equals to 17. So y of 0 equals to, I mean, the other color, y of 0 equals to 2, another y of 0 equals to 2, and y prime of 0 that equals to 17. All right? Okay, here we go. Yes. Oh, so we can easily take the Laplace transform of t squared, and then at the once we're done, once we get that function of s, we're gonna shift it s minus 3 units. All right. So that's just I mean, if you can do it like in your head and go straight to the next shot, you can do it. But that's a notation we discussed last time. So we can easily visualize because there's like a lot going on when we transform one of these, So, okay. So this is s squared um, y of s minus s times y of 0, which is 2. That's actually 2s, all right? Minus y prime of 0, which is 17. Minus, okay, let me distribute this. Negative 6s y of s. And what was y of 0? Wasn't that 2? So that's 2 gets multiplied with negative 6 to get negative 12. Well, let me do, yeah, actually, no, let me do, okay. Let me keep the brackets. S y of s minus 2. And then distribute in another step. Plus 9 y of s equals to the transform of t squared, that's the exponent, factorial over the new variable s increased by 1 power, which in this case is cubed. And then we're going to s minus 3. We're going to shift it later, all right? Okay, so let's keep arranging the equation. So that is s squared y of s minus 2s minus 17 minus 6s y of s plus 12, okay, plus 9y, y of s, equals to 2 factorial, which is simply 2, divided by the quantity cubed that got shifted, which is s minus 3 cubed. All right? So the rest of the problem is to solve, oh, well, first of all, solve an algebraic equation for y of s, and then find the inverse transform. Well, okay, so number one, let me highlight all the terms containing the y of s. Those are the terms that we're going to keep on the left-hand side of the equation, along with their corresponding signs, of course. And, okay, this looks like a times. It's a minus, right? Okay, so everything else, I'm going to move it to the right-hand side of the equation to begin with. So what is this 12 minus 17? Well, let me actually combine terms first. So this will be 12 minus 17, is that negative 5? And then negative 2s. And then notice I highlighted the terms containing the y of s. So I can simply factor it out. That's s squared minus 6s plus 9, okay, minus 2s minus 5 equals to 2 over s minus 3 quantity cubed. All right. Okay, actually, if you observe the left-hand side, that s squared minus 6s plus 9, it's also a perfect square trinomial. So let me actually factor it out. Y of s times s minus 3 quantity squared. And I'm going to move at once these two terms to the right-hand side. That equals 2s plus 5 plus 2 over s minus 3 quantity cubed. All right. And well, to solve for y of s, let me actually multiply both sides by 1 over s minus 3 quantity squared. Okay. And that actually leaves y of s finally. Right. Y of s, which is okay, I'm gonna multiply. Okay, check this out. This 2s plus 5 is the same as saying 2s plus 5 divided by 1 as a single fraction. That's to multiply these guys right here. All right. So what is this going to be? Well, this will be 2s plus 5 divided by s minus 3 quantity squared plus 2 divided by s minus 5 quantity to the fifth power. No, not at minus 5, it's minus 3, right? And, okay. So at this point, we may go ahead and find the inverse transform of this, all right? Okay, so check this out. So number one, uh, the inverse transform of y of s will be the inverse transform of 2s plus 5 over s minus 3 squared plus the inverse transform of 2 over s minus 3 to the fifth power. All right. So actually, if you recognize the first term, didn't we already find the inverse transform of that one? That was example number 2, in fact. All right. So note from 2a specifically, 2a. Okay. What do we get here? From 2a, we get 2e to the, what is that? E to the negative 2t. No, wait. No, e to the 3t. And that plus 11 t e to the 3t. All right. So that's the inverse transform from part A. The second term, actually, what can we do about this one? Okay, so I'm going to take out these two out of the fraction. That'll be plus 2 times the inverse transform of, actually, no, yes, plus 2 times the inverse transform of 1 over s minus 3. Well, actually, I'm going to write instead s to the fifth power, okay, And then I'm going to shift s to s minus 3. Again, so we can easily find the inverse transform of 1 over s to the fifth power, and then simply, what is that? Simply shift at the very end by multiplying by that exponential factor. Okay, number one, let's talk about this inverse. Let me change color and do some work on the side. Let's recall that the inverse transform of what is that? N factorial over s to the n plus 1 equals t to the n, all right? Or the Laplace transform of t to the n equals n factorial over s raised to the n plus 1. Now, here's the thing, be careful. So it seems like 5 equals to n plus 1, right? In our example here. So that means n equals to 4. So that means we would need to multiply, or rather, we wish we had a 4 factorial here. We can make our wish come true, just divide 1 out, right? Okay, but what's 4 factorial? Is that 4 times 2, which is 12 times 2, which is 24 times 1, which is 24? Okay, so, well, actually, this would be, okay, so 2 over 24, okay, and this is t to the fourth power, and in this case, because of the translation, e to the negative e to the 3t. The other two terms just go to e to the 3t plus 11t e to the 3t, and this is y of t, because the inverse of y of s is y of t, right? Final answer. Well, actually, I'm going to simplify this 2 over 24 as a 1 over 12, right? So, so it's one example of how we use the first translation theorem on solving a differential equation using the Laplace transform. Well, I mean, again, it relies on the same rules, on the same transform, and whenever required, whenever applicable, make sure to shift. Well, when doing the transform, shift accordingly. When finding the inverse, the shifted, make sure to multiply by an exponential factor that reflects the translation s minus a. All right. Okay. So let's move on to the next topic, which is, well, this is preliminary to get to the second translation theorem. Let's talk about the unit step function, also known as a Heaviside function. Okay, so function or a unit step function denoted with this fancy u of t minus a is defined in the following way as a piecewise function. So it's 0 has a value of 0 between 0 and any value of t, and then it has a value of 1 for that particular value inclusive and on. Or if we have a more composite or more elaborate uh, function, well, as you will see, we're going to get, okay? And its Laplace transform is given by Laplace of u of t minus a equals e to the negative as divided by s. In fact, we already did something like this when we found the Laplace transform of piecewise continuous function. And then I mentioned that we were going to get more in depth into these kind of functions later. Well, this is where we're gonna do that, all right? Okay, guys. So, alternatively, there is a notation. Rather than writing the t minus a, all you can do is simply write the u, and as a subscript, whatever translation is reflected on the function, right? And simply parenthesis c. So either way is just fine. All right. Well, so some of these functions, I'm not gonna lie, those are gonna be a little tricky to obtain before we are even able to get their Laplace transform. But I'm gonna do a bunch of exercise, a bunch of examples, many examples. First of all, let's prove this result. Okay, so let's find the transform of u of u of t minus a. Okay, which is what is that? The integral from 0 to infinity of e to the negative st u of t minus a. But how are we going to integrate that? Well, what do we have? We have a piecewise function, right? So from this piecewise function, uh, what's the value of the function between 0 and a? Well, in this case, we're going to split this into two integrals. One integral for the function f of t equals to 0 between 0 and a. Okay, so that's the integral from 0 to a of e to the negative st. Well, in this case, between 0 and a, what's the value of the function? Isn't that the horizontal line y equals to 0? Okay, dt plus the integral from a to infinity of e to the negative st. And what's the value of the function at that point? Isn't that 1 unit? There's a jump of 1 unit dt. Of course, this means the first term is just going to go to 0 because the integral of something times 0, that's the integral of 0, and the integral of 0 from 0 to a, well, that's going to give us a 0. All right? So what else? The integral from a to infinity of negative st with respect to t. So this will be, first of all, limit as b approaches infinity. I'm going to set up this as an improper integral from a to b, essentially, of e to the negative st dt. All right, this will be the limit as b approaches infinity of the integral of e to the negative st with respect to t. Here, the dummy variable here is t. That negative s will be the constant, right? So that'll be, yes, negative e to the negative st over s, okay, evaluated between a and b. So limit as b approaches infinity of, actually, let me take out the negative outside. Okay, I'm going to take the negative and the s in the denominator. So that negative 1 over s, I'm going to take it outside of the limit because what we're evaluating is in terms of a function of t. All right? Okay, so that leaves us with e to the negative st um, minus, or actually minus sb rather, minus e to the negative sa. Okay? But okay, let's talk about the first term. Where is this quantity going to go as b approaches infinity? Where did that go? 0, right? 0. Now that's going to leave us with negative e to the negative sa. Now be careful, negative times the negative we had before. What is that? It's positive. Well, I'm going to write the positive sign. That is simply e to the as instead of sa over s, which is that result, isn't it? And that's the end of the proof, right? Well, let's have a look at some examples. Let's talk about these jump discontinuities, how and what do they represent? Well, okay, guys, you can think of these piecewise functions as signals being modeled, or maybe lights turning on and off, you know? For instance, what do we have? So in this case, we care about the domain from 0 to positive infinity. We don't care about the negative domain. We only care about the 0 and on. So to have a better overview of this function here, what's going on here? So we have the light off, okay? We have the light off between 0 and a, and then at a, boom, at time equals to a, boom, it's actually on by 1 unit. Well, so that you can think of this as the intensity of the light, if you will, or the intensity of the signal, depending on what would you like to relate it to. All right. Okay, so let's consider the function f of t equals to, okay, 0 if t is less than 0, but actually more properly, huh? So more properly, uh, this should have been instead, this inequality should have been 0 less than or equal t less than 3, all right? Because t less than 3 means also including the negatives. And again, we just want between 0 and on. Okay, so what does that mean? It means that between 0 and 3, our signal is 0, all right? And I'm going to put an open circle at 3, okay? What's going to happen here? So then between 3 and 5, we're going to have a signal or light with an intensity of 4. Okay. So I'm going to go up to 4, solid point here. Okay. And then I'm going to do a horizontal line, y equals to 4, but only between 3 and 5. All right, between 3 and 5. And at 5, what's going to happen? That a light with intensity equals to 4 or a signal with a signal of 4 is going to turn off, and then a new one will turn on, one with an intensity of 2 or one with a value of 2. Okay, so solid, and then simply goes on forever. All right? Okay. Now, what's going on here? So here, okay, so our focus is what happened at the values of t where we have the jumps here. So here at 3, we have a gain of a plus 4. However, at 5, we have a loss of 2 units, all right? So plus 4 and then minus 2, okay? Let's write this in terms of, what is that? In terms of a heaviside function. So you will always start with whatever you have first, all right? In this case, what we have first is 0, okay? So that means f of t equals to 0 plus, okay, at 3, all right? Let me open parentheses. And then u of t minus 3, all right? And then let me open parentheses, and then u of t minus 5, all right? This is to represent the two values of t where we're going to have some fluctuation in the signal or in the intensity of the light, however you want to think of this. So, okay, guys, what happens here? Again, so we have a signal with an intensity of 0 that actually turns off, but then at 3, actually, the signal with an intensity of 4 turns on. What do we do in this case? We subtract whatever we turn off from whatever turns on at that specific time, all right? So 4 minus 0, okay? So what happens at 3? Okay, think about 3 over here. All right? At 3, the one on the left turns off, the one on the right turns on. Subtract whatever you have on the left from what you have on the right. Okay? Now, what happens at 5, the next point where we have some a new switch, if you will. So, in this case, 4 turns off. So we will subtract 4 from whatever turns on, which is 2. Isn't it? All right. Now, okay, let's clean this up. You don't need a 0, so that's a 4. Oh, wait. F of t equals to, what is that? 4u of t minus 3, 2 minus 4 minus 2 times u of t minus 5, right? Are you guys following me with this? Is this making sense? Okay, well, now let's find the Laplace transform. We're gonna do a bunch of exercises, like I mentioned. I know. And the first time I got this, I was like, what the hell is this? But then it took me a while. Okay, so if it's taking you a while, it's normal. Okay, let's find the Laplace transform of this. So that is the Laplace of f. That is 4 times the Laplace of u of t minus 3 minus 2 times the Laplace of u of t minus 5. Okay, so I'm not going to do the integral anymore, guys. We already have a formula for this. e to the negative as over s. That's it. All right. Just identify the a. It's only the value at where we have our different switches. That's all we do. That's all we do. So this is big F of s. Okay. Equals to 4 e to the negative 3 s over s minus 2 times e to the negative 5 s over s. Final answer. That's it. Right. Let's have a look at more examples. All right. So for the next example, consider the function, this humongous function here. 0 between, again, I should have said more properly, 0, t, and 1. All right. Okay, so we have a function starting at 0, then becomes a 3, then becomes a 7, then goes down to 5, then goes up again to 6. Okay, so between 0 and 1, we have a solid open circle, right? And then between 1 and 3, we jump all the way to 3 and turns off at 3, right? And then we keep jumping actually all the way to 7, and that's going to be between 3 and 5, okay? And then we're going to go down to 5 units, solid, between 5 and 7, okay? And then 4 and then 6, one more jump, go up, okay? And then all the way to, I mean, this goes on forever, all right? So So that would be the growth of that crazy function we have. Okay, let's run its corresponding heaviside function. We cannot just take the transform of 0, the transform of 3. No, I mean, no, that's not how it works. Okay, so number one, what we have, okay, so at 1, okay, let's identify the different values of t where we have a jump, whether we gain something or we lose something, all right? So, number one, we have a jump of plus 3 units, and then we have another jump of plus 4 units, okay? And then we have a loss of, what is that, minus 2, and then a plus 1, all right? Okay, I mean, are you guys following me with these jumps and ups and downs? Okay, now let's write the heaviside function in terms of turning on and off. All right. Okay. Number one, start with your very first function. That is again a 0. So f of t equals to 0. Okay. Then we see the first jump. Where is that first jump at? Okay, plus open parentheses u of what is it? Uh, Actually, I'm gonna change notation here. Rather than using parentheses, u subscript 1 of t. So that's to indicate that we're gonna have a jump discontinuity at t equals to 1, rather than using the u of t minus 1. That's exactly the same. Again, I'm gonna use. I would like to use the different notation so you guys get used to the two of them. Okay, and then plus. I'm going to open parentheses and close parentheses. And then where's the next jump discontinuity? At 3. And then plus. I'm going to continue down here. That is an open parentheses, close parentheses. U at where? At 5. Plus, open, close. U at 7. And let's talk about whatever we turn on versus whatever we turn off. Okay, what happens at 1? The 0 turns off, okay? So that means we subtract 0 from whatever the value we have to the right of 1, which is what? 3? 3 minus 0. And then what's next? Okay, let me make more space here. There we go. And then what happens at 3? Our signal of 3 turns off, so subtract 3 from whatever's next, which is 7. All right? Are you guys following me so far? Okay. What's next? At 5. What happens at 5? Oh, the 7 turns off, so we're going to subtract 7 from what's next? 5? 5 minus 7. And then what's next? At 7, we turn off our signal of 5, so subtract 5 from whatever's next, which is 6, okay? Let's simplify these guys right here. So that'll be f of t equals to 0, we don't need the 0, 3, use of 1 of t plus 7 minus 3, that's plus 4, use of 3 of t plus 5 minus 7, it's actually negative 2 minus 2, u of 5, use of 5 of t, or which is the same as saying u of t minus 5, okay, plus 6 minus 5, which is actually another positive, that's simply 1. Maybe I don't need to write that 1, but I'm going to write it for a big reason. Check. U of 7 of use of 7 of t. Okay, guys, look at the coefficients of these unit step functions. Aren't those coincident with the values we either gain or lose at every single value of t where we see a jump discontinuity? Okay. So that was the same for the previous example. I believe I forgot to mention that. What do we have? 4, coefficient of 4, coefficient of negative 2. So plus 4 minus 2. Same. All right. Let's find the transform of for this one. So the Laplace transform, that'll be simply f of s. I'm not going to denote the big L. I mean, I'm just going to, because it's too many terms. All right. So this will be 3 times the coefficient 3 e to the subscript 1 means coefficient negative 1 over s plus 4 times e to the negative 3s over s minus 2 times e to the, in this case, is 5, negative 5s over s plus 1. I'm not going to write that 1. That is e to the negative 7s over s. So that is the transform for this one. Okay. All right. Okay. Now guys, we're going to do the reverse. And guys, this is usually the trickiest one. Okay, that's why I have like a couple of exercises, like two, I believe, or yeah, there's two also. Okay, now consider the heavy side function given by f of t equals to 2 minus 3 u of t minus 2 plus 4 u t u of t minus 5 minus 2 u of t minus 7. Well, at first glance, it's like, what the hell is that? And how are we going to go back to write it? Well, first of all, identify the values of t where we have a jump discontinuity. Those are given by the opposite in signs of the numbers that you see in parentheses or in the subscript of u, depending on the notation you have. All right? So let me do, okay. So number one, at 2. Oh, well, number one, where do we start? So we start at, this time we don't start at 0 like the previous exercises. This time we start with a signal of 2 units. And well, turn on 2 and turn it off when t equals to 2, right? Okay, how do we write the rest of the function? I mean, because f of t equals to 2, it's easy to plot. That's why, that's a horizontal line, y equal to 2. Of course, shortened by the condition, you know? Okay, again, remember, what do these coefficients mean? Those coefficients, if positive, gain, if negative, loss, all right? So that means I'm going to go down 3 units because of the negative 3. So that's 1, 2, 3. And then I'm going to turn on a signal with a value of negative 1. And what is that going to be? That's going to go between 2 all the way to the next value of t where we have a jump discontinuity, which is all the way to 5. Here is where we're going to turn it off. All right? And then what do we have? Okay, we have the 4. That means we're going to go 1, 2, 3, 4, turn it on, and come on, turn it on. Why not? Come on. There you go. Turn it on at 5 all the way to 7. Here is where we turn it off. And then what do? -2, we go down 2 units, turn on another signal, and in this case, boom, that one goes on forever. Right? Okay, so we have that function to find its transform already. I mean, we don't need to do anything else. However, they ask us to graph the function and, well, find the transform, but also express f of t as a piecewise function. Okay, so let's write that down. I'm going to write the function f of, oh, come on, f of t, that is, we start where? At 2, right? And that's 2 between 0 and, oh, excluding the 2. And then y equals -1 between 2 and 5, and then 3 between 5 and 7, and then what do we have? 1 bit for all values of t greater than or equal to 7. All right. Okay, let's find the transform. Okay, the transform of a constant, that is big F of s, first of all, the constant divided by s, all right? That's the transform of a number. And then minus 3 times e to the translation, e to the -2s divided by s, and then plus 4 times e to the translation, -5s over s, minus 2 e to the last translation, -7s divided by s. All right, that is our triangle. Okay. One more. One more. Okay. Okay, so the very last one, they're not asking us to find the transform. Only practice on how to go from heavy side to piecewise function, and of course, most importantly, graph it. I mean, if you want to take the transfer afterwards, well, that's up to you. That's fairly easy to do. I mean, there's not much to do. Okay, so number one, unlike the previous example, see how the previous example had a number, a number, I mean, a numerical term without a function u or a unit step function. This time, this means we start at 0, isn't it? We start at 0. And then what are the discontinuities or the jump discontinuities at 2, at 4, and a 6? All right. So we're going to start with a signal of 0 from the very beginning, and we're going to turn off that signal when t equals 2. Okay, so that is our signal described with this horizontal line. Well, do you see the coefficient of -2? Doesn't that mean loss? So go down 2 units, turn it on, and then keep going from 2 all the way to 4, and turn it off at 4. And then we have a +5. That means we have a gain of 5 units. So that's 1, 2, 3, 4, 5. Turn it on, and then go all the way from 4 to 6. Okay, and turn it off at 6. Finally, we have a drop or a loss of 2 units. So that is 1, 2. Turn it on here, solve it, and then just go all the way to infinity. All right. That means let's actually write the piecewise function f of t. That is 0 between 0 and 2. And then what's next? -2 between 2 and 4. And then what do we have? 3 units, a signal of 3 units between 4 and 6. And finally, a signal of 1 unit between 6 and on. All right, so for t greater than or equal to 6. Okay. And again, you don't have to find a transform for this one, but I mean, I'll leave it to you as an exercise on your leisure time. Okay. So guys, these are the kind of functions we're going to work on when it comes to the second translation theorem. This is not yet the theorem. This is just the tool that we need to work with these functions with these continuities. So far, I mean, up to this point, we have found Laplace transforms of continuous functions, of nice and smooth continuous functions between zero and infinity, like the elementary functions of such like polynomials, exponentials of base e, sines, cosine, and their corresponding hyperbolic. We're going to get into other weird functions in this case, okay? All right. But I mean, the functions I just showed you here are fairly simple functions just to get the hang of it. Let's generalize this because what if our piecewise function is no longer function as nice as this one with all horizontal lines? What if you had, say, a trigonometric function and then a horizontal line, maybe then a cubic, maybe a decaying exponential? Well, how do we work with those? Okay, so that's what the second translation theorem is about. And in this case, that is what we call a translation on the t-axis, as opposed to the previous theorem, which was the translation on the on the s-axis. Okay, so just to give you the heads up, uh, what did we do in the previous theorem? We found the transform of the elementary function. All right. Then whatever we obtained, we just translated to s minus or shifted s minus a. But we did the translation in the world of s. With this second translation theorem, not for the direct transform, for the inverse transform, we will find the inverse of some function of s to obtain back a function of t. And that is where we're going to do the translation on the t-axis. You'll see how it's that going to work. Okay, guys. So number one, uh, well, that's actually what this text is. I just summarized it, right? So the theorem tells us that if f of s equals to the Laplace transform of f of t and a is greater than zero, of course, we're looking at values where we have some discontinuities in the positive t-axis, right? So we're not caring about negative. That's why we need this a to be greater than zero. Okay, so now we're going to find the Laplace transform of some function with the same translation as whatever the unit step function we're being multiplied with. We multiply that with. What is the transform of that function? Whatever f of s times e to the negative as. So it's no longer going to be that f of s. It's just going to be whatever the transform of the function we have, but initially we had what? 1 over s because we were just transforming constant functions. So if you want to generalize this function as a piecewise function, f of t minus a times u of t minus a, as a piecewise function, I would say this is 0 between 0 and a, and then at a, for t greater than or equal to a, we're going to have some function f of t minus a, all right? And that is where it's going to get a little tricky here. Okay, let me prove this result quickly. So we want to find the transform of f of t minus a of times u of t minus a. That is the integral from 0 to infinity, again, going back to the definition of the Laplace transform. That is e to the negative st, okay, times f of t minus a, u of t minus a, dt. All right. Well, what are we going to do here? So we're going to replace f of t minus a, u of t minus a with our piecewise definition. Again, this improper integral will be broken up into two pieces. An integral that goes between 0 and a, whatever that a is, which is going to be e to the negative st. But a, what's the value of this function between 0 and a? Isn't that 0 again? Okay, 0 dt plus the integral from a to infinity of e to the negative st times what's the value of the function between a and infinity? That is before t greater than or equal a, essential. Isn't that f of t minus a? So f of t minus a. All right, dt. Okay, guys, to evaluate this integral, I'm going to do a substitution. I'm going to set u equals to t minus a, du equals to dt. And at the same time, I'm going to set t, okay? I'm going to set t equals to u plus a. All right? So here we go. Check this out. This will be the integral from, okay, the integral from a t minus a. Essentially, that's going to be the integral because, oh, do you guys agree that when changing the limits of integration, u of 0, oh, wait, no, u of a. U of a will be a minus a, which is 0. So now the lower limit is going to go to 0. So that's going to spawn an integral from 0 to infinity, which is going to take us to the definition of the Laplace transform again. And well, what about u at infinity? I mean, infinity minus a, subtracting a from infinity is not going to do any harm. So that remains infinity. All right. So this is e to the negative s times, what is that? U plus a. All right. Times f of t minus a, which we said is u. That's f of u du. All right. So multiplication of exponentials, right? What do we have? An addition of exponents, multiply the exponentials. This will be the integral from 0 to infinity of e to the negative su times e to the negative sa and f of u du. All right? Okay, in this case, what's the variable? Isn't that u? Everything else you can take it outside of the integral. That is this s e to the s minus a, e to the negative, I mean, e to the negative sa, not s minus a, e to the negative sa. Integral from 0 to infinity of e to the negative su, f of u, du. Okay? I mean, guys, isn't that integral the definition of the Laplace transform? I mean, uh, yeah, it should be it because this is a numerical integral when we this is a definite integral, and it doesn't matter what variable do you use for a definite integral, it's going to give us exactly the same value. You can use a function of t as the original theorem, a function of u, a function of emoji if you want. It's going to give us the exact same result. So this will be e to the negative sa Laplace of f of u, right? Which is, guess what? What's the Laplace of a function of whatever dummy variable? It's simply big F of s. Anyway, it doesn't matter if you take the Laplace transform of a function of t or a function of x or a function of whatever, it's still going to give you a function of s, e to the negative times e to the negative sa. That's how. All right? That's how. All right, well, let's use this result now. Okay, guys. Now let's get away from constant function. Now let's make this heaviside function more interesting, so to speak. What do we have? Okay, f of t equals this piecewise function, which is the diagonal line t, but that's only between 0 and 2. So that means we start at the origin, solid point. Okay, wait, what's going on? Why is this not writing? Okay, so solid at the origin, and well, that's 1, 1, 2, 2, but turn it off at the point 2, 2. All right. So now we have a signal in the form of a diagonal line, no longer just a horizontal line. And then what happens? Turns off at 0, turns off to 0 from 2 and on. So it's 0, it's off from after 2 seconds or minutes or hours, however context behind it is, which we don't have. Okay. So, okay, let's write the heaviside function for this piecewise function and graph. So number one, again, regardless of what you have at the very beginning, that's what you started with. So you start with a signal on in the form of the diagonal line y equals to t. So f of t equals to start with t. And then, A, where do we have continuity? Isn't that at 2? Okay, so I'm going to set plus parentheses u of t minus 2. Do we have another jump discontinuity? I believe that's the only one, right? Okay, what happens at 2? At 2, there's a newborn signal of 0, okay? So that's the 0, but we subtract whatever dies at 2, which is the diagonal line. All right, so 0 minus t, okay, which will be equals to t minus, rather, t u of t minus 2. All right? And we would believe we're done, right? But no, check this out. Check. What about this translation? Again, we're trying to find the Laplace transform of a function that has the same translation as its unit step function. So watch out for that. We're not done yet. Careful here. Okay? So that means we wish that t were t minus 2. Well, we can make our wish come true again. Because we can. Minus t minus 2 plus 2, right? U of t minus 2. Okay, let's group these two. All right, that's actually going to coincide with the t minus 2, and the other one is just going to be a constant multiplying with the u of t minus 2. All right. So watch out with that one. I was all right. Careful, right? All right, so f of t equals to, well, okay, this t, we don't need to translate it, careful, because that t is just a loner term. It's not being multiplied by a unit step function. That is t, uh, check. We're going to distribute this whole t minus 2 and these two with the u of t minus 2. So this will be minus t minus 2 u of t minus 2 plus 2 u of t minus 2. All right? And we're ready to find the transform of this function. Okay, so, okay, guys, here's the tricky part of the problem. Okay, so this is the transform of t, that's 1 over s squared. That is one integer more than it originally came from. Of course, I mean, in the numerator, there's a 1 factorial, but 1 factorial equals to 1. So we don't need to write that one. Okay, so what are we really finding the transform of? I know there's a minus 2. Do we find that the Laplace transform of t minus 2? No, that's only a translation. Okay, guys, check this out. Suppose you don't have any of this. What's the Laplace transform of t? Again, isn't that again 1 over s plus 2? Okay, now on pretend. Okay, let me put this back on. Okay, so that's minus 1 over s squared. And then what's the translation? T minus 2, so we multiply by e to the negative 2s. All right, what's the transform of a number? The number divided by s multiplied by e to the same translation 2s. Final answer. All right.
Is that still FFT or is that supposed to be big F of S?
Big F of s. Thank you. Thank you. Big F of s. It matters. Thank you. Thank you. Oh, the next one. Yes, you're gonna like the next one. Okay, guys, the next one. What do we have? So consider the function piecewise function f of t equal to 0 between, oh, again, I keep forgetting. I should have edited the notes. This should supposed to be 0 and 4, all right? And then t squared between for greater than or equal to 4, all right? Okay, so this is what we're going to do. So it's going to be a signal or a graph of the function y equals to 0, starting at the origin 0, and then we're going to turn it off at 4, all right? And then what happened? A new signal is turned on, a signal of the form t squared. But guys, what's the value of t squared at t equals to 4? Isn't that 16? Okay, so, oh shoot, we have one, two, three. Okay, well, let's make it the necessary adjustments. Okay, let's make each mark right here. Let's make them 8, 16, and 24. All right. So at t equals to 4, that's 4 squared, which equals 16, isn't it? So that's this point. And then I'm going to give it the shape of the parabola. All right. Of an opening up parabola. Okay, so what do we have? We have a signal with a switch at 4. What happens at 4? The 0 turns off, the quadratic turns on. Okay? With a little trick here. Okay? So f of t equals to, where do we start at? Don't we start at 0 again with a signal of 0? Write it down. That's fine. After a while, you may not need it to write it. All right? I mean, I just want to do it for every single exercise. So to be consistent with everything we do. Plus, what happens at 4? Do you guys agree t squared minus 0? So t squared, which is whatever turns on, minus whatever we turn off, which is a 0, where when you at t minus 4. Okay, I mean, this simplifies to the following. T squared u of t minus 4. I mean, again, what's a translation here? T minus 4, all right? Here, check. It's not. This guy right here, wish it were T minus 4. We can make our wish come true. Let me actually do some side strip for this one, okay? This one is going to be a little tricky one, okay? So I'm going to write t squared, okay? T squared, do you guys agree this is the same as saying t minus 4 plus 4? Quantity squared, I mean, I'm subtracting and adding 4. I'm essentially keeping that 0 there, all right? And then what am I going to do? I'm going to highlight whatever works for our translation, okay? Whatever works for our translation with one color and whatever doesn't with another color, okay? What am I going to do here? I'm going to expand the binomial. Remember a binomial squared? This would be t minus 4 squared plus 2 times the product of the two, t minus 4 times 4 plus the square of the second one, right? Okay. I believe that's actually going to do it, you know? That'll be, can we just simplify? That'll be t minus 4 quantity squared plus 2 times 4, which is 8, times t minus 4 plus 16. And yeah, all this crazy humongous quantity is equivalent to t squared, except the way we wrote it here, it's to serve a big purpose, to make it look like a translated function at t minus 4, so we can find the Laplace transform of it, all right? So we're going to end up with three terms. So guys, here's the thing. The number of functions we have called um, in the piecewise function doesn't have necessarily a relation of on the number of terms in our heaviside function. for a constant one, that kind of that there were kind of a relation. Here, not really. Now, think about doing the same, but for t cubed. That's going to yield a total of four terms. I'm pretty sure, a bunch of terms. So, and still, we just have two functions in our piecewise functions. I mean, just so it's not so you think about it, right? Okay. So, let me go back to blue. So f of t equals to bracket, all right? Bracket t minus 4 quantity squared plus 8 times t minus 4 plus 16 bracket. All of this is shifted at t minus 4. All right? Okay, guys, let's find the Laplace transform of this. Again, let's pretend, okay? Let's pretend you don't have this guy right here. You don't have the minus 4. You don't have the minus 4. Essentially, you're just finding the Laplace transform of t squared, t and 16. That's all you're doing. Okay, let me go back in time, right? And have it the way it was, right? Back in time, the way it was. Let's unpretend what we pretended, you know? So, is that an actual word anyway? Or did I just make a new measure? Okay. Well, but you guys get my meaning, right? Okay. It should be written, right? Okay, so let's find the transform big F of S. Okay, what's the transform of t squared without the minus 4? That is 2 factorial over s cubed e to the translation negative 4s, all right? Plus 8 times the Laplace transform of t, which is just s squared, e to the translation at negative 4, at 4, you know? And the Laplace transform of a number is just the number divided by, what is that? S, e to the negative 4s. All right. Final answer. Well, 2 factorial, come on, that's just 2, right? Crazy, isn't it? Is it making sense anyway? It's weird, I know, but hopefully makes sense. Okay. Okay, next one. I think the next one, and we call it yes.
Why did the translation apply to the 16?
Oh, because it's also being multiplied with the unit step function at that particular time. Okay, guys, the next one. Be careful with the next one. Okay, so what do we have for the next one? Consider the function f of t equals to cosine of 2t for t less than 2 pi, actually more properly between 0 and 2 pi, turns on at 0, turns off at 2 pi, and then we have 0, okay? So let's graph the cosine function, okay? I mean, a cosine function looks like this. I mean, cosine 2t. That's just half of the period at 2 pi, isn't it? Because the period for that one would be what? Pi, right? The period of cosine 2t, the period would be, what was that? 2 pi over the number that multiplies. So that'll be, no, wait. Uh, well, anyway. Okay, yeah. Okay, so let's see about this. So then what happens? This. Okay. So f of t. Where do we start at? Cosine 2t. All right. And then plus what happens at 2 pi? All right. What happens at 2 pi? Turn off, turn on, and turn off. All right. U of t minus 2 pi. Okay. What do we turn on at 2 pi? Isn't that do we turn off the 0 and turn off the cosine 2t? All right. Okay, check this out. F of t equals to cosine 2t minus cosine 2t u of t minus 2. And again, guys, look at the cosine 2t. We wish we had it at 2 at t minus 2 pi, right? Again, we can make our wish come true. However, check this one out because What did we do with the previous exam? Didn't we add and subtract whatever number helps us get the translation? But guys, it turns out that the cosine function is 2 pi periodic. So you can simply subtract the 2 pi, and that is not going to affect the value of the function, right? Because whatever input t you substitute in that function, it's going to be coterminal if it's minus 2 pi, and also the plus. I mean, you can still do the minus 2 pi plus 2 pi, but in this case, it's not necessary. All right. So again, note. Let's write our wish. Wish it were t minus 2 pi. Let's make our wish come true. Mhm. Cosine 2t minus cosine of 2 times t minus 2 pi. Yes, I could write the plus 2 pi, but again, and let me write that note. Let me make some room first of all. Okay, write a note, make some room. And okay, u of t minus 2 pi. Okay, so as a side note here, no need, no need to add 2 pi because periodicity of cosine function, right? That's why we don't need it in this case. Okay? Or if we had the sine function, same. We don't need it. All right. That's not for all angles, you know. So, but well, in this case, it works for this one. Okay, so let's find the Laplace transform for this function. So, big F of S. The transform of cosine isn't that S over S squared plus the number that multiplies t quantity squared, which is 4. All right. Now again, here is where we pretend on pretend. Okay, we don't have the unit step function. Find the Laplace transform of cosine to t, which is actually that same one. Okay, let's unpretend. There we go. Okay, that'll be plus, or rather minus, s over s squared plus 4. And in this case, e to the negative translation 2 pi t. No, 2 pi s. Final answer.